All right, guys, today we're going to be talking about testing a claim about a mean when we don't know sigma. So if we don't know the population standard deviation, we're going to have to use a t-test instead of a z. Similar requirements, simple random sample, and either normally distributed or n is greater than 30. So for both a z and a t, one of these must be true. If they're both true, great. If one of them's true, great. If neither one are true, you can't do a z or a t. Again, I'm not going to try and trick you there. So all the tests I give you will be doable. We're going to have to look at the t-distribution chart. So that'll be a little different. And with the t-distribution, p-value is a lot more complicated to find than for the z table. So we use the student t-distribution when sigma, our population standard deviation, is not known, and either or both of these conditions are satisfied, just like we just said. Normally distributed, greater than 30 for n. So the p-value test, if you're using a TI, it's fine. We'll pop it out for you. But if you're doing it on your own, if you're doing it by hand, then you'll probably want to stick with the traditional method as much as possible. On your tests, I'll only have you do the p-value once at most for a t-value, for a t-hypothesis test. And again, we're just not going to have a quiz this week. So M&Ms again. They're weighing 13 red M&Ms, and here's the data set. Those weights in grams have a mean of that and a standard deviation of that. Notice very carefully that those M&Ms have a standard deviation, not the population of the M&Ms in the bag have a standard deviation. This is the sample standard deviation, S. Make sure you're able to distinguish between S and sigma. If you can't do that, you won't know if you use a Z or a T, and that'll throw you all off. The net weight of the contents are 396.9. Divide that by 465 to get what each M&M should weigh on average. Use the sample data with a 0.05 significance level to test the claim of a production manager that M&Ms have a mean that is actually greater than that. So I'm going to go ahead and highlight that. That's my claim. The claim gives you your hypotheses. So start there. Use traditional method. Okay, so this example, we're just going to do the traditional method. We're going to actually look specifically at p-value on another example. So traditional method, nothing's really changed. Write down your null and your alternative. Greater than, well, so mu is greater than 0.8535. I know that's in my alternative because it doesn't have equality in it. So that's where my claim is. My claim is in the alternative. That means my null is less than or equal to. And again, we have the data set here, so we could calculate X bar, but they give it to us. So we're going to use what they give us. 13 red M&Ms, so N is 13. X bar is 0.8635. And here's where it's extraordinarily important. Make sure you use the proper symbol for your standard deviation. If it's a sample standard deviation, those weights have a blah and a standard deviation of this. Those weights, the sample weights, have a standard deviation. That makes it S, sample standard deviation. If we're talking about the bag of M&Ms, the whole bag, that would be the population standard deviation. That would be a sigma. So that will determine the difference between a Z and a T test right there. Alexa, bedroom lights on. Okay. So there's S. We know that alpha is 0.05. So we've got our hypotheses. Hello. Hi, Alana. It's treatment time, my love. So we have our hypotheses, claims in the alternative. Alternative says greater than, that makes a right tail. So we're going to first use the chart. Also, pretty much everybody, you're just going to use the chart. TI users, if you have that program, the inverse T program, you can use that. I have to reprogram it into my calculator because that kind of open new calculator. But my 84 does have it built in there innately, so it'll just be slightly different procedure. You can watch the video on that. So, but let's do the chart. Okay, it's a right tail, that makes it one tail. So I'm going to look over here. T distribution. That's what we're doing. Okay, first thing we need is the test statistic. I'm coming up here, right here. Notice this time, instead of a Z score, we have a T score because we're using the T distribution. And come back here. Remember that your critical values and your test statistics, they're both going to be either Z or T scores, but they have different names. They're test statistic and critical values. So make sure you call them by those names instead of just Z scores or Z values. So that's the formula we need for the test statistic. I'll do it in blue. So T in this case equals, and we know it's a T because look right here, we have S, we don't have sigma. 0.8635 minus 0.8535. S is 0.0576 over square root of n. Okay. If we calculate that, just going to type in the Casio real quick. So that'll give us our test statistic T. And again, it's going to be the area under the curve, but it's not the normal curve, it's the T curve. You don't have a T distribution, cumulative T distribution function on here. So we're just going to be doing this by hand. 0.6, well, we can still go 3 decimal places to be safe. Let's see what the chart has. If we look at the chart, they go 3 decimal places. Oh, that's chi-square, sorry. 3 decimal places. So we're going to go 4 decimal places to be safe. So 0.625, well, 0.6260 is what we're going to use. So we're always going to go to 4 decimal places. Okay. TI users, I'll do the whole thing on the TI in a minute. Right now, I'm going to get the critical values, again, using the chart. The Casio doesn't have any way of doing it on the calculator, and you had to write that program for the TI, if you have a TI. So let's do the curve sketch. Again, 0 is going to be in the middle. That's not changing. Our test statistic is this. We need to get our critical values. I'll put them this color. Look at our tail. It's a right tail. that means a one tail and a positive. So the t-chart is different. Remember for Z, we just looked up, the alpha value and we were done with it. Let's look at the t-chart for a minute. So it tells you area in one tail, area in two tails. Look at what we have. We have one tail and the alpha is 0.05. One tail, so we're using this top column, this top row, 0.05. So we're going to look in this column right here. Okay. Now, for the left side, the degrees of freedom. Let me write that down because you probably forgot from whenever we did confidence intervals. Degrees of freedom equals n minus 1. There are cases when that's not true, but for this class, for our one sample, our one population, our one proportions, we're just doing n minus 1. That's all we need. Degrees of freedom is n minus 1. For this class, always. So n was 13, that means we need to go to 12. So here's 0.05. We're looking in this column, we're going to go to 12. This row where they intersect, that's my critical value, 1.782. Okay, so now let's sketch that. 1.782, I'll put that right here, to the right of the mean somewhere. And it's a right tail, so I'm shading in to the right. If we need a left tail, we take this value here and just make it negative. It's just the negative of it. These are all basically right tails, whereas the Z chart is a left tail always. Okay, now we plot our test statistic. T is 0.62. I'm gonna stick it right there. Okay, it's outside of the rejection region. So from here on, it's the same thing. We fail to reject the null. Since we fail to reject the null, and our claim was in the alternative, there is not enough evidence to support the claim that M&Ms have a mean that is greater, weight greater or whatever than 0.8535 grams. So that'll be our conclusion. On the test, I believe I'm going to get you to do these on paper and pencil and just take a picture, upload it to Moodle. That way, you can actually do your curve sketch and it will just be easier that way. Yeah, no quiz, otherwise it would just been the same as last week's basically. So again, p-value, we're doing that on the next problem. It's a whole procedure on its own. So let's look at the TI. Now, if you are using the TI, you can run your t-test to the same place. Test number 2 is a t-test. We have stats, not data, to give us the information. Well, actually, we have data here. We could put that in and it'll give it to us, but it's easier just to type in the stats since that is also given to us. 0.8535. X bar is 0.8635. S, notice they even have the S here, not the sigma, is 0.0576. And N was 13. And in this case, we have a right tail. Again, that always comes from the alternative hypothesis. By the way, I'm recording this on Zoom this time. It seemed to make smaller videos and seem to be generally better. So let's hope it works. Okay, it gives me my critical value, 0.625, well, 6260, same thing. It does give you the p-value. PI users, go for the p-value, it's easier. Same rules. P is greater than alpha, we fail to reject the null. Done. Write down your conclusion. Now you can get the critical value if you go to your program, and I don't have it on this one. I thought I saved that calculator, but I didn't. I have a quadratic formula program instead, but remember you wrote that inverse T program, just run it, 0.05 for alpha, and your degrees of freedom would be 12. My PI84 though does have an inverse T, so I can do it on here. 0.05, my degrees of freedom are 12, and it takes a second. And it gave me the negative, but remember we're doing a right tail, so we just use the positive. 1.7823, very close to what the chart has. Okay, look at the p-value now. Okay, p-values are a lot more complicated to calculate for a t-test. We're actually going to find a range of values, not necessarily just one most of the time. It's either be greater than this thing or less than this thing. So we're going to find the p-value for that previous problem. It's a right tail test, and the number of degrees of freedom is 12. Okay, so we look in 12, and we try and find our test statistic in that row. So we're looking for 0.626 in the 12 row. As you can see, we don't have anything close to that, right? So what we have to do is say, okay, it's going to be over here to the right of this number. So if we look up here, it's one tail, one tail. So we're looking at this right here, 0.10. So we can say that P is greater than 0.10. That's all we can say. And if you look at it, it's pretty far away from here, so you can guess that it's going to be significantly further from 0.10, but you can't get an exact value at all. So all we can do is say T is greater than 0.10. If we compare that to alpha, our alpha value is 0.05, P is greater than alpha, we reject the null. Sorry, we fail to reject the null. So you gotta look and see where you're gonna be at. So we use the degrees of freedom 12 because our n was 13, degrees of freedom is 12. We look for the number closest to our test statistic. Usually we between two numbers. So let's say we had 1.5 for our test statistic in the 12 degrees of freedom. Then we could say P is between 0.05 and 0.1. If P was bigger than 3.055, let's say P was 5, then we'd say P is less than 0.005. So to the left is the smaller numbers, to the right is the bigger numbers for alpha, for your area. So depending on where your p-value lands, it'll either be between two of these, or two of these if it's a two-tail, or it'll be greater than this one if it's smaller than these numbers, or it'll be larger than this one if it's larger than these numbers. And you know, if it's a left tail, you'd imagine all these as negatives. I find it easiest to just ignore the negative and just, you know, see where we go. Okay. In previous tests, baseballs were dropped 24 feet onto a concrete surface. And they balanced an average of 92.84 inches. So basically, all I'm going to do is go through some examples, finding critical values, test statistics, p-value, and just doing the hypothesis test, because really there's nothing new to learn except we have one new formula and we're using that same chart we did before with the t's. So this is our new formula. We're using the t distribution like when we did confidence intervals. So nothing's really changed. And they bounced an average of that. In a test sample of 40 new balls, the bounce heights had a mean of that, a standard deviation of that. So again, we have to determine, is this a Z or a T? In a sample, the bounce height had a mean of this and a standard deviation of that. That's in a sample. That makes this a T. That's supposed to be a T, not an A. Use a 0.05 significance level to determine whether there's sufficient evidence to support the claim that new balls have a bounce height with a mean different from what that says. So again, I like to determine whether I'm using a Z or a T before I start writing everything down over here. If you write everything down, you write a sigma, well, then you know it's a Z. If you write an S, then you know it's a T. I like to kind of figure it out beforehand so I know what I'm writing. It's 40 new balls, so that criteria is taken care of. Again, we're just going to assume the criteria is good. We can do these. I'm not going to give you any that you cannot do. Different, as a symbol is not equal to. Um, 92.84. Maybe try the same number there. N was 40. X bar, 92.67. The standard deviation of the sample, S, was 1.79. We're using an alpha of 0.05. And let's look. It is a T, because we have S, not sigma. It's a two-tail. So, we're going to look at the area in two tails. We don't have to worry about cutting it in half. The chart does that for us. Makes it a little easier for us to look at. But we do need a calculator test statistics. Let's go ahead and do that. Okay, so if you don't remember that formula, it's right here. You are allowed your formula sheet. So you don't have to memorize it. (92.62) minus 92.84 over 1.79 over square root of 40. Okay. And we type that in. PIUs, again, this will just spit, I already spit it out for you. So we get a negative 0.7773. Okay. So I'm going to do the traditional method. Well, let me show you on the TI. So stat, test, 92.84. X bar was 92.67. S was 1.79. N was 40. And we have a two tail. That matters for P. Your test statistic will be the same. Okay, so somewhere I typed something in wrong. Ninety-two point 92.84, so 40. Okay. Let me see what I typed in here. 92.84, 92.67, 1. Okay, guys, give me a minute. I'm just gonna pause the video right here and figure out what I did wrong. Okay, sorry about that, guys. I'm back. I found my mistake right here. I put 92.67. Should be 92.62. Okay. And then they do agree. We have the same test statistic here. All right. So I'm going to do the traditional method first. It's easier if you don't have a TI. TIs, we can already see what the p-value is. It's going to be 0.22. But for non-TI users, let's just go ahead and do the traditional method. So I got 0 there in the middle. My critical value, let me grab that. It's a two tail. So I'll look at my T distribution. Area in two tails. Area in two tails is 0.05. So we're going to use right here, 0.05. Notice that corresponds to the area in one tail of 0.025. All they did was they just made it a little easier for us to look at. Because if we were doing it in one tail, we'd have to cut alpha in half, which would be 0.025. We could still just use these values up here. Depending on what kind of T distribution table you have, you might see it where it just has the one tail. And it could have a lot more than just these particular alpha values in particular areas. But this particular table we're using, the one that's been dropped up the Google Drive, and the one I printed out for you, splits it up for us, so it makes it a little easier to look at. Okay. So area in two tails right here, 0.05. And we have N is 40, so we have 39 degrees of freedom. Now, if we look at this chart, see, it's the middle column. It doesn't have 39. It has 38 and it has 40. Now, if you're up here where it's 50 and 55 and that, you go to whichever one's closer. Just, yeah, well, it really doesn't matter, but let's just do this. Go to the lower number always. That'll be safer. If we go to the lower number, it has a bigger critical value, which would mean that the data would have to be more extreme for us to be able to, reject the null or fail to reject the null. So really it just doesn't matter. We can go up, we can go down. It's not going to make that big of a difference, especially with that test statistic of negative 0.773. But ideally we'd want the more extreme values. Anyway, so we're in this middle column. So we actually use one of these. I'm going to go with the 38, the 2.024. That's my critical value. So I'm going to put that right here. Yeah, I'll just do that. That's 2.024. Now, I also have the two tail, negative 2.024. And we're just going to shade those tails and look at our test statistic. Our test statistic, put it in red, was negative 0.7773. That's right here. That means we fail to reject the null. It's outside the rejection region, we've got to reject the null. To calculate the p-value, okay, we've got this flow chart over here, but it's a little tricky to use with the t-distribution. Since the t-distribution already has our area split up for us, that's just what we're going to use. So we've got a two tail, or if we had, if we had a left tail, we just use the positives. If we have a right tail, we just do it as is, because this gives us the area to the right. And the distributions are symmetric. The T and Z distributions are both symmetric. So the area to the right of this 6 degrees of freedom, 3.707, the area to the right of that would be equal to the area to the left of negative 3.707. They're equal. So we can really just kind of ignore the negatives for p-value cases. But if we go back, we're looking at 38 because we didn't have 39 degrees of freedom. And we're looking for our test statistic. It's negative 0.7773. So we're looking for 0.7773, positive. Well, it's not here, it's out here somewhere. Okay. So it's greater than this 0.20 number. If you remember on the flow chart, we had to find the area to the left or the right and double it and all that good stuff. On the t-distribution, it already has it doubled for us. So don't double it again. What we can say is right here, p is greater than 0.20. That's all we can say from the chart. So p is greater than 0.20. TI can give us a more accurate answer. It's 0.22. Okay. So the p-value is 0.2208, et cetera, et cetera, et cetera. If you're using a calculator, that's fine. If you're using TI calculator. If you're not, use the chart and just find it on the chart. Just find your degrees of freedom and whatever is closest to your test statistic. Same thing though, p is greater than alpha. So we're going to fail to reject the null. And our claim, well, I didn't write down what my claim was, did I? The new balls have bounce heights with a mean different. So that claim is mean alternative. Claims in the alternative, we don't reject the null. There is not enough evidence to support the claim that the balls have a different bounce height. Bounce height that is different from 92.84, something like that it said. The new balls have bounce heights with mean different from yada yada yada. And that the new balls have a bounce height, mean bounce height that is different from whatever they just said. So remember these right here, these conclusions, that's the answer to these hypothesis tests. That's the conclusion. On your test though, I'm going to expect to see all of this. Now, again, I'm not necessarily going to make you do the p-value. I'll have you calculate the p-value one, but it's just going to be calculate the p-value for this test statistic. So TI users, you won't even be able to type in the numbers because you're not going to have the numbers. You're going to have to use the chart and estimate the p-value. So there'd be one like that on the test, and only one. Yeah, okay. Next. Analysis of last digits of sample data values sometimes reveals whether the data have been accurately measured or reported. When single digits 0 through 9 are randomly selected with replacement, the mean should be 4.50. The standard deviation should be 2.87. Reported data are often rounded so the last digits disproportionately include more zeros and fives. Use the last digits in the reported lengths of the 73 home runs hit by Barry Bonds in 2001 to test the claim that they come from a population with a mean of 4.50. Use a 0.05 significance level, and this tells us these home runs have a mean of 1.753. It does appear the distances were accurately measured, or did they kind of round to nice numbers? So test the claim. Let's find that. Test the claim that they come from a population with a mean of 4.50. There it is. Mean of 4.50. That's an equal to problem. That's going in my null. I'll go ahead and write down now so I don't forget. That's my claim. So my alternative is not equal to. That makes it a two-tailed test. Everything else is from here. Let's just see what we've got. Let's write down our information. N is 73. What else do we need? We've got mu, standard deviation of 2.87. What has a standard deviation of 2.87? When single digits 0 through 9 are randomly selected with replacement, the mean should be between 4.50 and the standard deviation should be 2.87. That's the population of numbers 0 through 9, not this sample of 73 home runs. That's a sigma. So what does that mean for us? It's a z-test. You have to be able to identify when we have a z and when we have a t. And you do that by reading carefully what your values are. So this is our mu. This is our sigma, not S, sigma, making it a z-test. So we're going to do what we did Tuesday, Monday, whatever day that was. We're given X bar, 1.753. So that means, we look on our formula sheet, right here, we're using a z-test. So that's the formula we're using to get our test statistic. Of course, TI users just type in all the info when you're done, just hit stat test 1 instead of stat test 2. Alpha, 0.05. So in this problem here, we have a z-test going on. Z equals our critical value. 1.753 minus 4.50 over the standard deviation, 2.87 over the square root of n, 73. So that gives us a z-test statistic. So we're going to use the z table here. Sorry, now this one you could use a normal CDF to get the area. Go back and watch Monday's videos if you want to. 2.87 square root of 73. Oh my goodness, negative 8.1778. Yeah, you should know what that means already. Okay, that's our test statistic. It's a big one. So let's go ahead and get the p-value first. It's a z-test. Let's get the p-value. It's easier. So let me look. Am I finding p-values? Okay, first, what kind of tail are we looking at? Two-tail. Is it to the left or the right? It's a big freaking negative number, so that's definitely to the left. We find the area to the left of the test statistic and double it. So you should all know what the area to the left of negative 0.8 blah, blah, blah is. On the chart, it's going to be 0.0001. Yeah. 3 zeros. Anything smaller than negative 3.5 has, just use 0.001, and that's still going to be huge. Using a TI, we're going to get a much more accurate and much smaller p-value. But for this, it's a two-tail, so we get the area to the left, 0.0001. So we have to double it, whole times 2. 0.0002 is the p-value used from the chart. Excuse me. With the calculator, the TI-83, we'll get a much more accurate p-value. Let's do that now. Okay. Stat test. It's a z-test, people. We have stats, 4.5 for the mean of the population. 0.87, 1.753, and 73. Two-tail. Notice it's two-tail. And yeah, okay, look at that p-value. It's a decimal followed by 15 zeros. 15. And then a 3. We can round that up to 3. P is less than alpha. P is less than alpha, we reject the null. Claim is in the null. So there's enough evidence to reject the claim. And what was the claim? They come from a population with a mean of 4.50. I'll just take the numbers. Come from a population with a mean of 4.50. So yeah, we got that. That's the answer. We could do the critical value. I mean, inverse norm, use the Z table. This lesson is primarily focused on the T table, the T distribution. So I'm just going to leave it at that. But you have to be able to identify whether you have a Z or a T. That's based solely on whether or not you have sigma. This case gave us sigma. That means it's a Z. Do the Z test. And answer the question, based on the results, does it appear that distances were accurately measured? Nah. They rounded them things. Birth weights, crackheads, or their babies. In a study of prenatal cocaine use on infants, the following sample data were obtained for birth weight. Okay, so they straight up tell you S right here, just spits it out at you. Use a 0.01 significance level to test the claim that weights of babies born to crackheads have a mean that is less than the mean of non-crackhead babies. Well, start with your hypotheses. Less than. That's going right there in the alternative. That's my claim. Greater than or equal to. That's my null. This is going to be a left tail test based on the alternative. It gives us the info. It tells us to use an alpha of 0.01. Yeah. So let's see, it's S. That makes it a T. Distribution. So it's X bar minus mu over S 245. 245, yeah. Make sure there wasn't a decimal in there. Over square root of n. That gives us a test statistic of another huge freaking test statistic, negative 8.6, blah, 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 blah. So without doing any work, I'm going to say we're rejecting the null there because that's a pretty dang big test statistic. Pretty big negative test statistic, and we're having a left tail. Well, let's do the work. Let's see where what goes. Find the critical value. Okay, alpha is 0.01, one tail. N is 190, so we're going to go for 189 degrees of freedom. I'm pretty sure they're not going to have that exact one, so whatever's closest. Yeah, okay. Huh. Let me get a different chart just for this problem. 190. Is that? Oh, wait. Chi-square, you nincompoop. Here it is. T distribution. 190, that's closer to 200 than 100, so let's go with that one. Okay, we got to go with whatever it's closest to. We should use 189 if we had a more accurate chart. We don't. We're going to use what it's closest to. It's a lot closer to 200 than it is to 100. That's what we're going to go with. 0.01 in one tail. 0.01 in one tail, that's the second column. So 2.345. My critical value, 2.345. However, it's a left tail, so we got to make that negative. So I'm going to stick that right here. I just put critical value there. Yeah, so I have to write that number in a really small spot. And then I'm gonna use blue, and I'm gonna write test statistic there, T. The test statistic is in the rejection region. We reject the null. That means there is enough evidence to support the claim that crackhead babies have a mean that is less than 3 grams, have a mean birth weight that is less than 3,103 grams. Based on the results, does it appear that birth weights are affected by cocaine use? Yes, crackheads have lighter babies. That's not a good thing. Okay. I'm sure politically speaking, I should not use the word crackhead, but whatever. Critical value, test statistic, that's the traditional method. Let's look at the p-value. Negative 0.86. Negative 8.6, wow. So I'm gonna look for 8.6. That's over here. That's to the left, so that's less than, smaller. So how many tails do we have again? One tail. That's the record, funny. Yeah, second column, okay. So it's to the left of 0.005. So I'm gonna say P is less than 0.005. I hope we get one that's between soon. Otherwise I'll have to pull another random example out of my butt. I'm gonna watch this video anyway. So another thing, P is less than alpha, reject the null. Same thing. PI users, let's see just how small that P is. We know it's got to be less than 0.005. Let's see where we're at here. Number 2, a t-test, 3103. Whoa. Whatever. Yeah. Type in all this stuff. Left tail. Okay. PI is like, dude, your p-value is 0. It's just way, way too small to even give you any decimals in scientific notation. So I'm pretty sure 0 is less than your alpha value, whatever that may be. So 0 is smaller than 0.005, so we were right there. Okay. It's a really tiny p-value there. So remember, the p-value can tell you exactly how sure you are of your results. A p-value of 0 says there almost isn't a single bit of doubt that whatever you were claiming, whatever your alternative is true, and that whatever your null is that's wrong. So the alternative with a p-value of 0 is pretty certain, like 99.29% certain. All right. Let me see how many more of these we got. Okay, just 2 more. Hopefully the p-value will be between a couple things so I can show you that. Let's go ahead and do this FICO score one. Random sample, again, it gives us S, so we know it's a T. If you want to, you can pause the screen and read it yourself. I'm just going to highlight the importance. Claim that these credit ratings are from a population with a mean that is equal to 700. Equal to That's my null equals 700. My mean does. H1. Mean would not equal 700. That's my alternative. And the null is my claim. Okay, it gives us our useful info up there. .3 if you can't read my handwriting, it's right there. And we're using alpha 0.05. Two-tail test going on here. Calculate, that's an S, so I'm going to calculate my t value, my test statistic, t. .3 minus 700 over 95.9, which is over square root of 18. Type it in. Okay, here's a decent one. Negative 1.7563. At 1.7563. Oops. No, 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 no. Please don't. Cancel, don't shut down. Okay, we just fall. All right, I think we're good now. We're back. Where was I? Where'd I go? Video. There we are. Sorry. Give me a minute. Oops. Good enough. Yeah. So that's my t test statistic. Let's go ahead and do the critical find the critical value. Sketch it. Alpha is 0.05 and two tails. Two tails, 0.05, that's the middle column. And we have n is 18. 18 minus 1 is 17. So we're going to look at 17 degrees of freedom here. Middle column, 2.110. Okay. So my critical value is 2.110. And I'm going to plot that on here. And I'm just going to abbreviate that critical value. That's 2.110. Now it's a two tail, so I also have the negative 2.110. A negative critical value. Okay. Now I'm going to plot my test statistic. Let's see, this is 2.110. Let me actually write that down for this side. My test statistic is between that and 0, right there. That means it's not in the rejection region, so we fail to reject the null. So that's the traditional method. Again, I like it better for p-tests. If we're getting the p-value, we're going to look up 1.7563 with 17 degrees of freedom. I'm looking in this row. That didn't work. I'm looking at this row right here, 17. I need to find 1.75. Oh, hey, it's going to be between these two guys, right? Really close to this one, but between them. We have a two-tail. So the area in two tails right here is where we're looking. That means P is between 0.05 and 0.10, pretty close to 0.10. So P is less than 0.10. And it's also greater than 0.05. Our alpha value is 0.05, so P is greater than alpha. We fail to reject, yeah. P is greater than alpha. We fail to reject the null. So either way we do it, we fail to reject the null. So I'll walk you through this part one more time. So P is based on your test statistic, 1.7563. That's between these two numbers. We have to look for 17 degrees of freedom. Where is it at? Between these two numbers. Those two numbers have an area in two tails between 0.05 and 0.1. So P's got to be somewhere between there. That's all we can say using the p-values. But that's enough information to tell us that P is greater than alpha. P is greater than 0.05. Okay. So there is not enough evidence to reject the claim that these credit ratings are from a population with a mean that is equal to 700. These credit ratings are in a population with a mean of 700. So that'll be my conclusion there. PI users, we can see exactly where, exactly what our p-value is. It should lie between 0.05 and 0.10. Let's see where exactly it lies. Again, it's a t distribution. $100. 95.9, 18. That's a two-tail. So yeah, it's 0.097. That's between these two numbers. I told you it was really close to 0.10. Sure enough, it's really close to 0.10, but not quite there. And yes, it does tell you your test statistic right there. So that's a p-value. Again, I just prefer just finding the critical value, use it, do the traditional method, sketch it. Okay, we got this one. We actually have to find the mean of all that. You should know how to do that in whatever calculator you're using, or any calculator. Just add them up and divide by how many ever there are. In this case, there's 3, 6, 7, 8, 16. Different cereals are randomly selected and the sugar content is obtained from each cereal. Use a 0.05 significance test to claim that the mean for all zeros is less than 0.3 grams. So use 0.05 significance, that's alpha, to test the claim that less than 0.03. So less than goes in my alternative. Mean less than 0.3. Greater than or equal to would be my null. In 1, 2, 3, 4, 5, 6, 7, 8, 16. X bar. There's no sigma, so S. Yeah. We do have alpha. Wow. That's not alpha. We got to find X bar and S using this data set. It's last one. I'll just go ahead and do it on both calculators. PI users, just type it in there and be done with it. Stat, edit, clear that first list. 0.03, 0.24, 0.3, 0.47, 0.43. Hopefully I don't screw up. Oops, I just screwed up. Okay, so that's 17 right there is blank, so I have 16 numbers in there. Second mode to quit, go to my test, t-test. This time we're using data with a move of 0.3. List L1, frequency, keep that as 1. Tail, left. Calculate. And it gives us our mean and our standard deviation. .168. Again, I'm just going to go one decimal place further out than the data set. But if I'm doing these calculations, I'm going to use the entire decimal using the store function. Don't round until the end if you can help it. TI users, though, you're done. You got a P of 0.45. That's greater than alpha. We fail to reject the null. Where's our claim? Our claim is right here. So we're going to, P is greater than alpha. We fail to reject the null. There's not enough evidence to support the claim. Okay, but let's do it. We got this info. I'll show you how to do that on the Casio now. Go to mode 3, one variable, type it in. and 0.43 lastly. And that's on 16, so we're good. 0.43. Hit the AC button right here. Go there. Notice we're still in stat mode, so we're going to go to Shift 1. We need some variables. What do we need? We need X bar first off, number 2. Whatever that is, I'm going to store it to A. Why not? You could do B, C, D, E, F, whatever, it doesn't matter. I'm going to store X bar to A. If that gives me. Losing battery, shoot. Stat, shift, stat, number 4. We also need our sample standard deviation right there. And if we compare that to the TI, that's the same thing. Notice we use SX. Even though it has an option of sigma, that's an estimation of sigma. Don't use it. Don't try and make it a Z test. No, you don't do that. Use this number and use the T test. And we're going to store that to B. Okay. So let me hurry because I'm running out of battery here on my AirPods. Let's do a little video. T is X bar. Again, in the calculator, I'm actually going to use the whole decimal number it gives me. But for writing down, I'm just going to use 3 decimal places. I'll do that in the Casio. Go to mode 1. X bar, I named that A. Let me just check. I don't remember. Yeah. And B for, yeah, okay. Yeah. So A is X bar. Sorry. B is S. And the square root of 16, you could just type 4 if you really wanted to. Negative, and if we compare that to TI, same thing. Oh, just turned off, of course. Negative 0.11923, negative 0.11923. So 0.1192. That's my test statistic, traditional method. I'm gonna find my critical value. It's a left tail. Left tail 0.05. One tail 0.05 is the second last column. N is 16, so my degrees of freedom is 15. 15 degrees of freedom. 15 degrees of freedom, second last column. That's my test, my critical value right there, 1.753. It's a left tail, so we make that negative. Negative 1.753. So I'll plot that right here. Shade the tail. Plot my test statistic, which you can see is going to be right there. I'm not in the rejection region, I'm going to fail to reject the null. TI users, remember, you're pretty much already done whenever you type it in because it gives you the p-value. We can get that next. Look up this 0.1192, the positive, with 15 degrees of freedom. 15 degrees of freedom, I can say p is greater than 0.10. So that means p is greater than alpha. So again, we're going to fail to reject the null. PI users can tell us exactly what that p-value is. 0.45, so that's a good bit bigger than 0.10. But using the chart, the best we can do is say it's bigger than 0.10. Yeah, let's write the conclusion down now. There is not enough evidence to support the claim that, whatever the claim was. Something about serial. The mean, I guess I could say sugar content, whatever. That the mean for all cereals is less than 0.3 grams. And that's it. So same basic process. First thing you're going to do, write down your hypotheses. Mark which one your claim is in. All that's based on this part right here. Test the claim, that. That tells you your hypotheses, that tells you where your claim's at. Then get the important information, however you have to do it. If it's got some data sets, you have to type the data in and figure out X bar and S. If they give you sigma, straight up, you know you're doing a Z test. If you're got sigma, Z test. If you don't have sigma, T test. So both of those are for the mean. All right, guys. Well, that's about it. I'll throw some homework in Google Drive later. Yeah, that'll do it.